I wanted to thank the organizers of both programs. It's very nice to be here and interact with both communities. I have to say, after 1 week, we had our first week of workshops. I'm already super tired, so I don't know how it's going to be at the end of the whole month, but let's see. Okay, so today I wanted to talk a little bit about recent results that we got on energy balance models and Koopman analysis of these models, and mixing basically Koopman and response theory. If you were at Valerio's talk on Friday, maybe you have seen a few of these things, but if you weren't there, welcome. And I hope I will be able to give a little bit more insights and a little bit more details on what we've been doing. So, incredibly short summary of what climate is. If you're a physicist or an applied mathematician, you would describe climate as a forced, dissipative, nonlinear, complex, and heterogeneous system kept out of equilibrium. So if you're a dynamical system person, you are very happy with climate because it has all the features that you love and makes it incredibly complex. Now, all these processes in the climate are actually driven by a simple picture, if you want, and I'm simplifying here. And the simple picture is the fact it's composed of 3 different features. The first one is that we have incoming solar radiation. So the sun is basically powering us. We have that the absorption of this energy is non-homogeneous in the climate. And then we have the fact that the Earth is basically embedded in space. So we're in contact with a very low temperature heat bath. And so we actually emit this energy back into space. And this picture is going to be relevant for the kind of model that we'll be looking at later, because it's an energy balance model and it tries to exactly model these dynamics. And this very simplified picture, though, drives all the processes in the climate system. And these processes are super complex. They span 15, even more, orders of magnitude in time, and similar in space. And here you can see what we call a Mitchell diagram. So this is a schematic diagram of what a power spectrum of a supposed climate signals will be. And so you can see this power spectrum has some peaks, but mostly it's like broad frequency. And you have subsystems that basically overlap in the power spectrum, so you don't really have timescale separation, and it's quite complicated. You have energy flowing in all directions. Then you have some peaks. This is basically daily and yearly regularity, but then you have other peaks which kind of represent quasi-regular behavior. And since the Industrial Revolution, we know that anthropogenic forcing, mostly CO2 emission in the atmosphere, they have had non-negligible impact on the climate system. So if you're a climate dynamic person, you go to the best model that you have available at the time, and you try to think about how does anthropogenic forcing CO2 emissions affect climate. And then you would do something like you think about some forcing protocols. So you think, okay, what you see here is basically, let me ramp the CO2 in my model by, let's say, 1% each year. And then we have a commitment to stop that CO2 emission when I reach basically double the CO2 level or quadruple the CO2 level. And in this case, you're interested in something like TCR, which is the transient climate response, which is basically the inertia and the timescales that the system has to adjust to this increase in CO2. And then the other quantity that people are very interested in is the ECS. Where is it? Basically the equilibrium climate sensitivity, which is this the statistical properties of the system when it has reached the new steady state, basically with a new level of CO2. And you can look at global observables, like here, average temperature, globally average temperature, or you can look at more specific dynamical processes with still like a global impact on the climate. So for example, the AMOC. The AMOC is, if you don't know what that is the Atlantic Meridional Overturning Circulation. It's a big circulation pattern in the ocean. And more or less the way it works, starting from the tropics, you have warm and salty water that gets transported with the Gulf Stream towards the northern Atlantic, basically here in the UK and further north. And this warm water becomes cold, very dense, and it starts sinking. And so you have deep water formation, and you keep having this kind of circulation pattern, extremely simplified here. And you can think about, okay, how does this circulation pattern change with climate change? And you can define some observables. So for example, here you see the AMOC strength. This is an observable that basically tells you how much circulation you have. And I don't want to get into the details of how it's defined. And then using response theory or using your models, you can kind of see what the response of this observable is. And Francesco here is one of the authors of this paper. And you can see that initially the AMOC strength kind of decreases. So there's a positive feedback, positive meaning like destabilizing feedback. So the strength of the AMOC is reducing. And then after some time, you have a restoring feedback that basically brings it up again until you reach a steady state, which is weaker than the original one. And good point. This is basically the same perturbation as before. 1% increase until you reach double the CO2 level. So you kind of expect a linear response regime. Exactly, but this brings me to the next point. Actually, this kind of destabilizing feedback is a precursor of a tipping point in a way. So other types of forcing, they lead you to a very nonlinear, very bad response. Excuse me. Yeah. And yeah, there's like if you want like social commitment to keep the CO2 levels. But actually, and this is the figure, I think, with different forcing scenarios, and here you can see three. These are more realistic if you want. The orange one, that's a sustainable CO2 forcing, meaning that we increase, but then we relax to basically current level of CO2. And then you have an intermediate forcing and a strong forcing. And here what you see is basically the AMOC strength. This is in a different model. And for each color, you see different lines. These are same forcing, but different initial conditions on the attractor. And you can see that the orange one, for example, it does decrease a little bit, but then it stabilizes, which is similar to what we were seeing before. For the very strong forcing, we have actually that trajectories tip towards a different state. So here you have a on state of the circulation. Circulation is very active. Here you have a very weakened or completely off circulation, depending on the model. And in intermediate scenario here, forcing scenario, you have some trajectories that tip and some other trajectories that this one wanders around for quite a long time. It looks like it's stabilizing on the on state, but actually tips on the off state. Ooh. And actually, if you're interested in this, Reich, a participant in our program, has given a talk. He gave a talk last week, very nice, so it's recorded, so you can have a look at that. But yeah, so this is just to highlight that the response is not as nice as I was showing before. Usually it's not smooth, sometimes it's not linear, but it can be quite drastic. And this is an example of what a tipping point in the climate system is. And unfortunately, it has been realized that tipping elements, there are multiple tipping elements in the climate system. And here I'm just illustrating a few. You have the Amazon rainforest dieback, you have the Greenland ice sheet loss, you have all sorts of them, all different. And what is problematic is probably if you might have a cascade of tipping points. So if one of these tipping elements tips, then it might lead to the tipping of another one. So there's a lot of interest in understanding tipping phenomena in the climate system. And the IPCC AR6 report defines tipping point as, you read it, a critical threshold beyond which a system reorganizes, often abruptly and or irreversibly. So this definition is somewhat similar to what you would have in a bifurcation of a dynamical system, which is something that we're kind of all used to. This definition is highly debated in climate, and Reich, the person that I was telling you before, his talk was all about why this definition is wrong. And you can kind of understand this because if you go back to the figure that I was showing before, if you concentrate on the green ones, they all have the same forcing scenario. So the critical threshold is somehow the same for all of them, but some tip and some don't. So this, and the abruptness is also something that you don't observe here. This trajectory will eventually tip, but it wanders around for a very long time. So where is the tipping happening? So you have all these sorts of different problems. And we have some hope, though, in a paper by Ashwin, Wieczorek, they were all participants to our program, and other people. They have identified different tipping mechanisms in dynamical systems. And these are the three ones: bifurcation tipping, noise-induced tipping, and rate tipping. And the classical picture that you have in a bifurcation tipping scenario is this one. You have somewhat of a multi-stable system. You have like a double well potential, for example, and you have two competing states. And as you change, as you have a very slow forcing that changes the dynamical landscape, you have that one state becomes less and less stable until it becomes less resilient, until it tips completely to the other states. This is what we call a bifurcation-induced tipping. And noise tipping is something where the dynamical landscape is not changing, but the noise, especially if it's Gaussian noise, will eventually lead to a transition to the other state. And in this case, you use the techniques like large deviation theory, or mostly that. And the third tipping scenario is a rate-induced tipping. This is a little bit more difficult to understand, but the idea is that you take the dynamical landscape and then you change it wildly. Like maybe you shift it this way, you shift it that way, until you put it back at the same place. And the system is not able to track all these changes. And this unlocks new types of phenomena, and you need to have different techniques to deal with these tippings. So in this talk, I will mostly be talking about bifurcation types of tipping. And despite these tippings being the most well understood, because you have bifurcation theory, you have all these things, nice things, in high dimension, you still have some problems, I would say. For example, the first problem is you don't have a double well potential. You have something that in this well, you have a much more non-trivial dynamics. So you might have a chaotic attractor, for example. You might have different timescales. So how does it work that way? The second point, which is maybe the main point of this talk, is, okay, as the system gets driven towards a tipping point, can you identify what the destabilizing physical process is? Or in other terms, can you identify what the best tipping observable is in this case? And then, of course, in climate and in most applications, you usually have spatially dependent fields. So you have something that depends on space, and you don't have observables. What I will try to show you today is that by using Koopman or Kolmogorov, if you're a stochastic person, analysis of signals, it gives you a rigorous but data-driven analysis of trajectory data that basically allows you to kind of respond to these questions. And just to give you an idea of the setting, there's not going to be many equations in this talk. Our mathematical framework is the following. We think that our system can be described by a set of stochastic differential equations. And in a climate sense, the deterministic dynamics is basically the resolved dynamics that you would have in a climate model. And then the noisy part is something that is subgrid. So it's the parameterizations that you include in the model that you don't resolve explicitly. And in this setting, we can define, actually, let's go back to the deterministic setting. You can define a Koopman or Kolmogorov flow or operator, which is this operator K here. The idea is you have an initial condition, x naught. you know that this deterministic dynamic has a flow, defines a flow that brings the initial condition to a final state. And then this operator here is the one that evolves in time observable. So if you have an observable, could be energy, could be vorticity, could be any kind of observable that you want, the operator brings it from the initial time to the final time. And it's defined that way. If you have a stochastic system, you can still define these types of operator, but you need to interpret them in an average sense, in a way. Because we know that given our initial conditions, you have different possible noise realizations. And the operator, basically, you can think of it as averaging over all these possible noisy trajectories. So it should be interpreted in a statistical sense. Why do we care about this? Since this operator is linear, even if the nonlinear dynamics, even if the underlying dynamics is very linear, then we can use all the linear algebra or spectral analysis type of results that we have. And in particular, the eigenfunctions of this operator can be identified as special observables of the system, mostly because they evolve in a very simple way. In this sense, in a statistical sense. And to be a little bit more precise, even though this is not mathematically rigorous, but it can be made rigorous, the point that I want to make here is that the spectral properties of this operator are related to correlations and power spectra that you see in climate signals. And in particular, that's the correlation function. If you think that you can decompose the two observables that you're interested in terms of the Koopman eigenfunctions, then it's super easy to see that you can break down the correlation function in exponentially decaying terms, given by, with the decay rate given by basically the Koopman eigenvalues. And then you have that, so the eigenvalues are decay rates, eigenfunctions are somehow these best observables, as I was telling you before, and the eigenmodes, which are these coefficients here, they basically tell you how much an eigenfunction affects a specific grid point, if you think of observables that are defined in space. But the point is, you have a bunch of eigenvalues. These eigenvalues here, the closer they are to the imaginary axis, then they give you resonances in the power spectrum and correlation functions. To make it more mathematically rigorous, but I don't want to show the maths here, if you assume that the stochastic differential equations define a hyperelliptic process, then you can get these results by basically doing a spectral decomposition of this Markov semigroup in L2 with respect to the invariant measure of the system. And then you make an assumption of quasi-compactness that basically tell you that at long times, at least, the discrete eigenvalues is what counts here. This is all very good. If we know the spectral properties of these operators, we know a lot of the system. And the problem is, how do we get these spectral properties of these operators? And when I was designing these slides, it's a bit ironic that I'm presenting this slide here, because I've been learning these techniques from people in this room. But the idea here is we want to estimate spectral properties of an infinite dimensional operator, but of course we need to somehow make it finite dimensional. And in fact, all these algorithms, more or less, they define a Galerkin approximation. So you basically approximate these operators using a set of dictionary functions that you design a priori. And there are, for high dimensional systems, in order to avoid the curse of dimensionality, you can define kernelized versions where the dictionary is not explicitly defined, but is just implicitly defined by the kernel. And without getting into the details, what you get usually is somewhat of a self-supervised method to extract these spectral properties from data. And the idea here is you have some fields, you pair these fields, you take one field at time 0, and you pair it with the field at time 0 plus delta t. You do this for all your fields, and you get this kind of regression problem and a minimization problem that allows you to get eigenfunctions, eigenmodes, eigenvalues, all the spectral properties that you want. And just to give you an idea of how this works, a simple toy example, you have the Lorentz system, which is chaotic. You add a little bit of noise, because that's the theory that we put ourselves in. And what you have is that you have all these eigenvalues. This is the complex plane. You have an eigenvalue in 0. This is just the static properties of the system, basically the invariant measure. And these eigenvalues here, instead, they give you the decay rates. And you have that you can see here basically the correlation functions of these Koopman modes. And you can see that some of them, like these two, they oscillate for quite a long time. This is a real one, so there are no oscillations, and so on and so forth. And the interesting thing is, if you take just the first, I don't remember how many here, but like the first few, you can approximate correlation functions of other observables, like for example, this is the Z observable quite well, especially in long time. And the interesting thing that one can learn from these modes as well is that they have a physical meaning. For example, this one, we noticed that this mode here, the subdominant one, has an imaginary frequency, a frequency that basically is the shortest UPO of the system. This is the AB UPO, so the one that tells you I'm in one lobe and then I'm going to the other lobe. So they have a physical meaning. And this eigenvalue here has something, its frequency is something like the turnover time of the weakly unstable fixed point in the lobes. So it basically tells you how much you turn around a lobe. And the point, yes. Yeah, this is basically the autocorrelation function of Z. In this case, but you could do the correlation function of Z and X, for example, that would still work. In this case, the Lorentz system, the most interesting correlation function is the one in Z, because it oscillates and it stays persistent for quite a long time. The others are kind of decay quite fast. And yeah, thank you. And the point that I want to make, and that it's related to the tipping point scenario. Gary, do you have a question? No. Well, no, it's true. Actually, I think in the paper we show X and Y as well. But I think I remember that this one stayed more persistent for a longer time. Yeah, it's not like incredible. But it does work in general for different observables. And the point that I want to make is that it doesn't work only on correlation functions, and this is the main point of the talk, and it's related to tipping points. It also works, these properties are related to response theory, so how the system responds to perturbation. So for example, if you take your set of stochastic differential equations, and now you perturb it, and this perturbation is time dependent, it can be quite complicated on the drift term, but it has to be small. So in a linear response regime, what you can say is take an observable, and you ask yourself, oh, what is the value of this observable in the perturbed state when I apply the perturbation? In a linear response regime, it tells you that the time-dependent value of this observable is the unperturbed one, plus a linear correction. And this linear correction can be written in quite a universal way as a Green's function, time convoluted with the time modulation of the perturbation. The idea here is, if you know the Green's function, you know everything in a linear response regime about the response of the system to different types of perturbations. And you can do all the machinery, there's lots of equations, but what you get is what we call the fluctuation dissipation theorem. And it tells you that the response, so basically the Green's function, can be written as a suitable correlation functions between two observables. So basically this is a fluctuation dissipation theorem. And these two observables are the observable of interest to you, so F, and also an intrinsic observable that one could call a response observable that is, if you have worked in this space, is quite terrible, and it's not very well defined, because For example, one thing is you don't know, this rho zero is the invariant measure of the invariant density of the system. You don't know this one for general non-equilibrium systems. But the idea is the same. If you know how to decompose this response observable in terms of Koopman eigenfunctions, so if you can get these coefficients here, then you can still reconstruct the correlation function, and thus you can reconstruct the Green's function as well. And we have a paper with also Matthew and Igor here, which basically tells you that you can do this from data. You have trajectory data, and from data you can get those gamma k. And the idea, without getting too much into the details, is that these observables is kind of bad, not very well behaved if you think of it as in a Lebesgue space, because the invariant density is defined in, it's not uniform with Lebesgue. It's concentrated in areas in the phase space. But if you think of it as if you do this approximation in a space that is not Lebesgue, so for example, weighted with respect to the invariant density, then that observable is kind of well behaved, and then you can reconstruct this from trajectory data. The details are in this paper. And the point that I want to make here is that if you see, as you change the parameters slowly, the sum of these resonances, the ones associated with those coefficient gamma k, they approach the imaginary axis, so the spectral gap goes to 0. Then you have a breakdown of linear response, you have an increase of correlations, and you have what we call a critical slowing down that can be, in theory, used as an early warning indicator. And just to give you some examples in low-dimensional systems, I usually don't show these slides, but I think Caroline worked on this map, and I've called this map Caroline's map for like 3 months. So this is a simple 1D chaotic map. We put ourselves in a situation where the invariant density looks like this, and we applied our algorithm, and we were able to reconstruct Green's function for different observables, terrible observables like this one, or a quadratic one, but periodic observables. We also applied this to other types of low-dimensional system. This is a generalized Arnold-Katz map. So it's the usual Arnold-Katz map plus a nonlinear term. I think Julia has worked a lot on this. The invariant density looks a little bit like that. So we put a little bit of noise. The invariant density is concentrating on those stripes at the bottom, and we can show that we can reconstruct with that algorithm perturbation to uniform perturbation, so you basically perturb the state space directly, or even parametric perturbation, so you change the parameter of the system, and you can do this. You can also do it from Lorentz, super confusing picture. We did a comparative study. Here we used Ulam, data-driven Ulam, EDMD, which is another algorithm with Chebyshev polynomials, KDMD with polynomials, KDMD with Gaussian. What you see is that you can still, with some differences, you can still reconstruct the Green's function of the system to general perturbations. But what I want to show you today really is this energy balance model, which Valerio also showed you a little bit. What is this model? Basically, it's a very, very simple model of the climate. You can think of it, it has only one spatial resolution, which is the meridional direction. And you can think of it as a model that describes the evolution in time of a zonally average temperature. So like a temperature in this direction. And it's very simple. It has 3 physical processes. One is meridional heat transport. So how much of this energy is transported along this direction. This is super simple. It's parameterized as a diffusive part. There's no fluid in this model, for example. There's no fluid dynamics, which is usually what transports the energy. Then we have one physical process, which is the absorbed shortwave radiation. So you have light coming from the sun, energy coming from the sun. This basically tells you how much of this energy you absorb. And then you have the outgoing long wave radiation. So how much of this energy you emit back in space. And also we add a little bit of noise with some properties, but it's not relevant here. And I just want to show you one thing. In this model, simple model, you also have We also model a greenhouse effect, which is given by this, this functional property here. But what is mostly relevant in this talk is that we have an albedo, ice albedo feedback. And this ice albedo feedback is super important in the climate. The albedo is basically how much of the energy that comes into the sun you basically reflect immediately. And it's defined here. And there is this positive feedback in the climate, which is called the ice albedo feedback, which is a destabilizing process, because if you get colder, the albedo increases, so you reflect even more, so you get colder, even colder and colder. So it kind of destabilizes the whole thing. And one can show that in this model, this feedback gives you bistability. So for a specific value of the solar irradiance, which is how much energy arrives on the climate, on the planet, one is basically current state, more or less. You have a bistable situation. So on the top branch, that's a warm state, the current state, but you also have a snowball state, in which the planet is completely iced. And I think this afternoon we have 3 talks about energy balance models. So if you're interested in these models, you can come to our afternoon session. But the idea is exactly this. You have bistability. And here what you see is the globally average temperature. And for mu equals to 1, so current states, this is how they look like. These states look like in space. You have the global average temperature looks something like this, warm state, similar in the cold state. And here at the bottom, you can see the albedo. And the interesting part of the albedo is in the warm state where we're at now. Then you see that as you go towards the North Pole, the albedo increases until you get to a maximum level, which is the level that the albedo has in the iced state. Okay, great. So we put ourselves in the warm state, current level of solar irradiance, and we have time evolution of our fields, of the warm field, and then we do our Koopman analysis. And this is KDMD with Gaussian kernel. What we see is these eigenvalues here. We have the usual one as 0, invariant measure, and then we have the other decaying rates. One, we observe that there's no complex, there's no imaginary part. So this was actually a result that was obtained by Michael Gill. It's mostly due to the fact that this model is super diffusive, but it was very nice to see that the algorithm would pick up on this. And so how do these eigenvalues look like? Sorry, eigenfunctions look like. And you know, eigenfunctions are defined in the phase space. This is a PDE, so it's infinite dimensional. Discretized is 200 dimensional. So you need to project it in some kind of space to visualize them. And in the past 15 years, people have introduced all sorts of dimension reduction observables. One of them is clearly the global average temperature. This is the observable that everyone talks about in energy balance model. But then people have also introduced another observable, which is the delta, the gradient of temperature between basically equator and poles. And this delta T basically tells you the non-equilibrium property of the system. And what you observe here is that the leading mode, it looks like, so on x-axis you have globally average temperature, y-axis you have delta T. The leading mode looks very much like it's picking up, it's linear in the globally average temperature, and there's no dependence on delta T. So we identified the leading mode as being the global average temperature. Then you have higher order modes of the same one, like Igor was saying on Friday. And then you have, in the 5th mode, you have some kind of mixed dependence. You still have some dependence on globally average temperature, but delta T appears, basically. So you have this kind of a hierarchy where you have the first mode is globally average temperature, and then you have something that depends on delta T. And so what was interesting to see is how do the spatial properties, the Koopman modes of this eigenfunction look like in space? And you have it here, the first mode, globally average temperature. It looks something like this. It's always positive. It's the blue line here. Always positive. It peaks in a region. And this region we can identify as the ice line, basically. So where the planet is becoming iced. So this is a season, it's a region of high sensitivity. And then the fifth mode, the second physical mode, has a Koopman mode that basically changes sign from negative to positive. And where it changes sign here, it's exactly in a region where the derivative of the heat flux, so the imbalance of the radiative budget, so where you have absorbed radiation and emitted radiation are equal. So you can see it here, and then it kind of tracks the ice line. So from just a Koopman analysis, you can get a lot of physical results on the model. Yeah. These are the eigenfunctions. These are the modes. Yes. Yeah, yeah. The modes, isn't that what a Koopman mode is? Yeah, so basically the eigenfunctions here are defined in the phase space, which would be like temperature at, yeah, in the temperature space, let's say. And we projected them in a two-dimensional space given by these two observables. These instead are exactly how much this eigenfunction affects points, grid points, basically. X is space in this case, yes. X is physical space, not phase space. Yes.
Bottom left figure.
Yep.
Is this the same for all state spaces X, or if you chose a different state space X, would this look different?
The state, what do you mean state? State space is T in this case, is the temperature.
Yeah, so if I chose like a cube from blue, a cube from, so you have.
So this is like the Koopman eigenfunction is defined on basically T, right?
Yes.
T, or the vector of T in the, and then.
And this is like the absolute amplitude.
Yeah.
My question is the bottom, is the blue line invariant to the state?
So so this one.
Yeah, because
So
plotting it respects.
yeah, so basically like here I have, let's say 0.2. I have a temperature defined in 0.2. So
Yes, that's the question is, I know X is domain.
yeah.
And I know the top is the eigenfunction, the function of state. And so my question is, implicitly, phi 1, the mode of phi 1 is a function of the state and the because it's the mode and the spatial dimension. So I'm asking if there's state dependence of the blue line. We can talk about this.
Okay, because so basically like you fix a point. I don't think I get the question, but we can talk about it.
Yeah, the chalkboard will help, I think.
Yes, so like if you take basically T at this point, so basically this is heavily projected, so I don't know exactly the one-to-one correspondence between blue and space, but it tells you how, let's say, how you decompose T at point 0.2 in terms of the Koopman eigenfunction. And those coefficients are exactly this coefficient here. That's what I'm plotting.
No,
See? Yeah? Okay, perfect. Okay, but we can talk about, like, I think it's because I showed like scalar observables before. This is like a vector observable in a way. But so what we tried is we have our spectral properties, we have our modes, can we reconstruct correlation properties? And we tried it. We tried with global observables, so like average temperature and the delta T, the gradient. And you have a time series, you get those correlation functions, and it does reconstruct quite well. But it also picks up spatially dependent correlation functions, so like in the space. So here you have space, then you have time, and you can see that somewhere, which, spoiler alert, is the ice line, you have most of the variance of the system. And then we tried also response experiments for this with the algorithm that I was showing before. This is a response to increasing CO2 forcing. You can see that you have polar amplification, which is what we expect when you have a change in radiative forcing. And it picks up kind of the spatial profile, and it also picks up the time scale as well. So what do we get from this analysis when we apply it to bifurcation types of tipping? Well, so we're at mu equals to 1 in the warm state. Now we reduce it and we're going towards the tipping point. What you can see is that all these modes, they're not all, yeah, you have critical slowing down. You can see that the modes from 1 to 4, which are the leading one and then the higher order harmonics of that one, they kind of increase, their time scale increases coherently. And those are, I remind you, those are related to the average, globally average temperature. So it kind of tells you that the best observables to pick to check the tipping is the global average observable. Then you also have the delta T, which is this mode here, lambda 5. It does experience critical slowing down, but not as much as the global average temperature. So if you were to pick that observable, you wouldn't see it as clearly. And so we also looked at the eigenfunctions, the leading eigenfunctions, the one associated with the global average temperature, closer to the tipping. And what we observe is it has a similar structure. But if you look at the Koopman mode, so how much it projects in space, let's say, you can see it still looks like it's peaked at the ice line, but it's much broader. So it feels, we were interpreting this in a way where we're saying that the instability is kind of becoming global. It is peaked at the ice line, but the whole system is feeling this instability and is about to get completely iced. And then we looked at response functions far from the tipping, which is what you saw before, and also close to the tipping. And you can see that there's much more complicated. And at short times, you still have the polar amplification. But at longer times, what you see is that it picks up a sensitivity along the ice line, which also the Koopman does, so that it tells you that at short times you have some kind of behavior, and at longer times the leading Koopman modes, the one related to the ice line, are the most relevant. So you can see that this kind of analysis captures heterogeneity of this sensitivity across time and space as well. And I reached my conclusions here. I want to show you, I think I kind of tried to show you that this Koopman analysis provides dynamically relevant modes for these eigenfunctions and Koopman modes for this model. They're useful for dimension reduction because this analysis kind of justifies why people have chosen those observables, globally average temperature and delta T. It does help you reconstruct correlation functions and CO2 forcing. And it also clarifies how to choose the best physical observable for some kind of tipping behavior. And so, for example, in this case, we were able to identify that the global average temperature was the best observable to pick. Something that I would like to do next, and if you have ideas, I'm very happy to take them as well, is this model is quite simple. It doesn't have fluid dynamics, which makes the analysis, even the Koopman analysis, much more complicated. What I would like to do is apply this to an intermediate complexity model, the PLASM, the planet simulator, look exactly at this type of bifurcation phenomenon, this snowball state, and see whether the modes and the eigenfunctions look similar. Because if they do, then it kind of gives you a dynamical interpretation of why these hierarchy of models are coherent. And then something that Valerio has mentioned on Friday, but he didn't have much time, we want to do what we call kind of Koopman detection and attribution. Detection and attribution is a statistical technique that basically allows you to link the observation of climate change towards statistical response to forcing, so basically to response theory. And Valerio and Michael have showed that you can actually frame this method in linear response theory. And the idea here is that, okay, if these fingerprints here are Green's function, basically, and we can decompose the Green's function into these modes, can we basically reframe detection and attribution in terms of these modes? But this is exactly, it's future work, so I will let you know in a few months. Thank you so much for listening.
Okay, do we have any questions for Nico?
Yeah, so I guess in terms of going up to higher complexity, you have, I guess you have to estimate this response observable. So do you have like a sense of as soon as you go to high dimensions, that becomes harder, right?
Yes.
Do you have like a sense of like,
Well, so the idea, what I would like to do here is getting this more intermediate complexity model, 10 to the 5 degrees of freedom. You have ocean, you have atmosphere, you have everything, but then you kind of, the observable that you choose are kind of similar to the Gill-Sellers model. So I would just get zonally average temperature. So you would have still this kind of band that I was showing before. So you have a much more complicated model, but then you zonally average, and then you resolve only this dimension, and hopefully you will end up with something similar for the Koopman analysis. So basically you do the Koopman analysis not on a full state space, but on projected observables.
Yeah, I have a question. Okay, so from my understanding, which is very basic, the having the stochastic part is essential.
Yeah.
Okay. In application to complex climate model, where does the stochasticity come from? Because there has been talking for decades at this point about introducing stochastic terms, stochastic parameterization, but to my knowledge, for example, standard CMIP models, they don't have it. And even when they will have it,
Not even in parameters? I think parameters.
I'm not sure that the standard runs, for example. I'm thinking about the hypothetically, applying this in the best possible. Not, of course, in plasma we can do it, but like strategically for the future, because it's not really something that, from what I know, is going to happen, or at least not something that in any case we will be able to write it as a binary process. Or these are like just numbers which are added asynchronously in time. It's
so what you can show 3 things here, I would say. Yeah, having nice noise like this, much more, I don't think it's going to happen. But stochastic parameterization, I thought there were in climate models. Even if the noise is not nice, a linear process, and it's a jump process, you can still get regularity of these response properties. And Valeria, I think, mentioned it on Friday. If you have diffusive and jump processes, you still get nice operators, which are going to be non-local, more complicated. I actually don't know. We used ULAM to estimate these properties. I don't know if that's the best way to do it, or if there are optimized way. But you do see this kind of modes and response. The other thing that I would say, maybe, this is very complicated, is if you look at the whole system and you have a deterministic dynamic, that's one perspective. But if you're looking at a subsystem, which is usually what you tend to have in climate, then you have a much more non-trivial dynamics. Usually you have fluctuations and memory, and it's debated whether you should, in some applications, you can ignore memory and you just have noise, which could help in this case. In other cases, you don't have noise and you have memory. So reduced order modeling also would go into that direction as well, but it is very complicated.
You are modeling a very complex system, so I think your operators, Koopman operators, can't be normal, right?
Yeah.
So how, what do you do? What hypotheses do you make to avoid running into big trouble? And if you can't avoid that, what are the most interesting spectral theoretic problems that need to be solved here?
Well, one part is the Koopman algorithms as well, which in this case, this is like the spectrum is well behaved, mostly because the
spectrum maybe yes, but the spectrum is not the
Yeah,
point then.
That's true. That is true. Here we're going kind of in an operational way. For example, robustness we've been assessing in very much in an operational way, changing parameters and seeing whether things persist. When you add fluid dynamics operators are not normal and much more complicated, yes, that's on the theoretical side, I think that's much more complicated. For the time being, I would like to just check whether this intermediate complexity model, the leading eigenfunctions look similar, but yeah, I don't know. That's quite complicated.
Perhaps I can comment. Igor and myself, we recently developed something called Marshall decomposition. So instead of eigenfunctions, we use like a flag of invariant subspaces. even orthonormal basis. And then instead of projecting onto eigenfunctions onto those subspaces.
Yeah,
So
still
if
you need to prove something there.
Yeah,
That would be interesting to talk.
Thanks. I'd be very much interested.
No, okay, then please.
Thank you so much.